If you've ever prepped for a coding interview, you know matrix problems are going to show up. But what if I told you that you don't need to memorize dozens of different solutions? Today, we're going to break down just 3 core patterns that will pretty much unlock any matrix question you're likely to face. And that's the big idea right here. Instead of cramming a dozen different algorithms, what if you could just master 3 fundamental ideas, 3 patterns that let you solve all of them? Well, that is exactly what we're about to do. So let's just forget about rote memorization. Our goal here is to actually master the logic behind rotating a matrix, spiraling through it, and zigzagging across its diagonals. Because once you get the pattern, you can handle any curveball they throw at you. Okay, let's jump right in with our first pattern. I like to call this one the turn, and it's all about the logic of a 90-degree clockwise rotation. You know, the easiest way to get your head around this is to forget about code for a second. Just picture a grid of numbers in your hands. If you physically pick it up and turn it 90 degrees to the right, what happens? Well, that top row is now standing up on the right side, becoming the new rightmost column. And the left column is now lying down on top. It's really as simple as that. So how does that physical turn translate into math? Well, here it is. An element that starts at row I and column J, it just moves to a new spot. The new row is just the old column J, and the new column is calculated from the old row I. This little formula is the entire secret sauce behind the rotation algorithm.
And for square matrices, this is key. There's this absolutely brilliant trick to do it in place without needing a whole new matrix. It's just 2 steps. First, you transpose it. That means you just flip it along its main diagonal, so every element at ij swaps with the one at ji. Then, you just go through and reverse every single row. Boom! That's it. A perfect 90-degree rotation. Now, this is a super important distinction you need to talk about in an interview. That 2-step trick we just saw, it uses constant extra memory. We call that O of 1, because we're just shuffling numbers around inside the original matrix. But if the matrix isn't a square, or you're not allowed to change the original, you have no choice but to create a whole new one, and that's going to cost you memory, O of m times n. All right, so we've nailed how to turn the matrix. Now let's talk about how to walk through it. Our second pattern is the peel, and this is your key to solving any kind of spiral traversal problem.
The idea here is actually really intuitive. Just think about an onion. How do you get to the middle? You peel off that outer layer, right? Then the next one, and the one after that. That is the exact logic we're going to use for a spiral traversal.
So to make that onion idea into an algorithm, we set up 4 pointers to define our layer: a top, a bottom, a left, and a right boundary. And we just walk along them in order. First, we go right across the top row, then down the right column, then left across the bottom, and finally up the left column back to the start. Once that's done, we just shrink our boundaries inward and do the whole thing again on the smaller matrix inside.
And that's the entire secret. The whole algorithm is just a loop that keeps going as long as your top boundary hasn't crossed your bottom one and your left hasn't crossed your right. Every time you peel a full layer, you just move those 4 boundaries inward by 1 and repeat the process. All right, time for our third and final pattern, the zigzag. This is the one that lets us navigate the matrix along its anti-diagonals in that classic back and forth motion. The mental model I love for this is a zipper. Seriously, think about it. You're pulling the slider and it's gathering up the elements one diagonal line at a time, weaving its way from corner to corner. So the real key to the zigzag pattern is a super simple mathematical property. For any element on the same anti-diagonal, if you add its row index I and its column index j, the sum is always the same. It's a constant. That one little insight makes the whole algorithm click. Because of that property, the logic becomes dead simple. We loop through all the possible diagonal sums, which we'll call D. And for each diagonal, we just check, is D even or odd? If it's even, we travel up and to the right. If it's odd, we travel down and to the left. That simple check on the sum creates the entire zigzag movement. It's that easy. Okay, so we've got our 3 patterns: the turn, the peel, and the zigzag. Now let's pull it all together and talk about how to really shine when you're explaining this stuff in an interview. And when you look at them side by side, something really cool emerges. Notice that? For their most efficient versions, they all have the exact same time complexity and the same auxiliary space complexity. This tells you they're all equally efficient, both in terms of speed and the extra memory they need. So why is the time complexity always theta of m times n? Well, it's because each of these patterns, the turn, the peel, and the zigzag, they're all just really clever ways of doing one simple thing:
visiting every single cell in the matrix exactly one time. No more, no less.
Now, what really sets a great candidate apart is showing that you've thought about the edge cases. These are the classic mistakes. Trying that in-place rotation trick on a rectangle, getting your spiral boundaries off by one, mixing up the even and odd logic for the zigzag, and the biggest one, forgetting to handle an empty matrix. If you can mention these proactively, you'll look like a pro.
And really, that's the big takeaway. It all boils down to two things. For rotation and zigzag, it's about mastering those index mappings. For the spiral, it's all about carefully managing your boundary conditions. Nail those two concepts, and you are good to go. So, you've got the patterns down, but here's a little challenge to make sure you really understand it. How would you change the peel pattern to traverse a matrix spirally, but in the opposite direction, counterclockwise? Think about it for a second. The answer is just reordering those 4 steps we talked about. Thanks for joining me.